Okay, very good afternoon to all of you. We are having at our premises a very eminent person to judge the final thesis of Miss Narmada, Dr. Bharat Bhushan Sharma. He is currently working in NIT Hamirpur as Associate Professor. Bharat Bhushan Sharma received his BTech degree in Electrical Engineering from Regional Engineering College Hamirpur in 1997. Further, he received his master's degree in Electronics and Control from BITS Pilani, Rajasthan in 1999 and PhD in Electrical Engineering from IIT Delhi in 2010. He has more than 25 years of teaching experience with NIT Hamirpur and has guided several PhD and master's students towards their dissertation thesis. He is presently working as an associate professor in Department of Electrical Engineering, NIT Hamirpur, Himachal Pradesh, India. He has served NIT Hamirpur at various academic administrative positions, including head of the Electrical Engineering Department, head Training and Placement Cell, NIT Hamirpur, controller of examination, associate dean, electrical infrastructure and maintenance, member of board of governance, BOG, NIT Hamirpur. His research interest mainly includes control and synchronization of nonlinear system, dynamics of chaotic system, design of nonlinear observers, and coordination and synchronization of network system. He has published more than 125 papers in various international journals and conferences of repute in these areas. He has been awarded ISTE Best Teacher Award twice in the year 2013-15 respectively. He is member of IEEE Control System Society, Institute of Engineer India and Robotics Society of India. So we welcome you. And with your permission, shall we start with the... Yes, please go ahead.
Thank you, sir. Good afternoon, panel members, external examiner and faculty. I'm Narmada. Today I'm going to give my Viva Voce, PhD Viva Voce presentation on design and analysis of optimized backstepping based controller for a class of fractional order chaotic system under the guidance of Dr. Anuj Jain sir, Professor, School of Electrical and Electronic Engineering, LPU, and Dr. Manoj Kumar Shukla sir, Assistant Professor, Department of Robotics and Automation, Symbiosis Institute of Technology, Pune. And these are the contents which I'm going to discuss now. Coming to motivation, most of the real-time systems, they are non-linear in nature and they exhibit uncertain behavior, uncertain dynamics. So because of which it becomes difficult to design a controller for non-linear systems. Linear control methods are available, but they do not perform well with the non-linear systems. So non-linear controllers were also developed, among which backstepping controller, it provides better results. But the problem with this backstepping controller is it requires most complete knowledge of the system. So this problem motivated to integrate a deep learning architecture, that is recurrent neural network architecture with backstepping control, to approximate the unknown nonlinearities present in the system. So this work mainly it focuses on the developing a backstepping based controller with RNN to achieve improved stability and performance of nonlinear systems. Coming to introduction, control of any system means adjusting the input so that we'll get the desired output. Two types, linear and nonlinear systems. The control methods which are designed for linear systems, they are applicable only for small range of operation, that is near equilibrium point. When the range of operation is large, that means when states of the system move away from the equilibrium point, in that case these linear control methods, they won't give better results. Their performance degrades. Why? Because they cannot compensate all the nonlinearities present in the system. So there is a need to design nonlinear controllers, especially for nonlinear systems. But before designing that, we have to mathematically model the nonlinear systems. For the mathematical model of nonlinear systems, integer order calculus can be used or fractional order calculus can be used. But this fractional order calculus, it gives better characteristics of, it is better to model the nonlinear system using fractional order calculus because it describes the complete nature of the system. The basic operator in fractional order calculus is dAt to the power of alpha, where A and T are the limits of operation and Q is the fractional order, and the value of Q lies in between 0 and 1 for fractional order. And if Q is greater than 0, it acts as a differential operator. If Q is less than 0, it acts as an integral operator. And the various control techniques available for nonlinear systems are feedback linearization control, sliding mode control, backstepping control, and dynamic surface control. These are the basic controlling mechanisms. In feedback linearization control, a nonlinear system is either partially or fully converted into a linear system so that we can apply linear controlling techniques. In sliding mode control, a surface or a hyperplane is defined where and a control law is also defined such that states of this system will move towards this surface and they will stay on that slide on that surface, or they will slide on that surface. That is why it is called as sliding mode control. Coming to backstepping control, it is a recursive procedure where for each and every state a control law is defined, which is called as virtual control law. And here actually when a virtual control law is defined, every time it has to step back and consider the error or in the previous control equation, and also the differentiation of previous virtual control law. And dynamic surface control is also called as backstepping dynamic surface control. It is an extension of backstepping control. In backstepping control, actually every time we need to differentiate the control laws, because of which the number of terms will increase, which leads to explosion of terms, and the computational complexity it increases. So to overcome this problem, in dynamic surface controller, first order low pass filters are used, the output of which is nothing but the approximation of differentiation of virtual control laws. But for lower order systems, we can use backstepping controller. As the order increases, we can use dynamic surface controller. When compared to dynamic surface controller, backstepping controller, it gives the better performance. Why? Because it takes the actual values of the differentiation of virtual control laws, whereas approximate values are used in dynamic surface control. So in this work, actually I have used backstepping controller because I have implemented the proposed controller on Geneseo TESI system, which is a third order system. And this is the literature survey I have done. In this, various papers are considered wherein the conventional or the basic nonlinear controllers are integrated with optimization techniques like reinforcement learning, neural network architecture, and also these controllers, the nonlinear controllers are integrated with fuzzy logic eco-state network. These controllers are used for the design of control laws, and the optimization technique and fuzzy logic, these are all used for the approximation of nonlinearities present in the system. So in the first paper, reinforcement learning strategy, which is a machine learning algorithm that is integrated with backstepping control. Backstepping controller, it designs the control law, and reinforcement learning is used for the approximation of nonlinearities present in the system. In reinforcement learning, actually agent continuously it interacts with the environment and it updates the parameters, and based on the decision either it gets the reward or punishment. Based on that, again it is going to continuously update the parameters till the error in the approximation is minimized. In the second paper, fuzzy control law is integrated with dynamic surface control technique. Here fuzzy control law is used for the approximation of nonlinearities present in this system. In the third paper, eco-state network is used. It is similar to that of recurrent neural network architecture, but here it consists of three layers: input layer, reservoir layer, which is the middle layer, and output layer. Here middle layer reservoirs weights are fixed, only output weights needs to be trained, because of which the computational complexity decreases. And in the last one, only sliding mode control is used in this work to minimize the tracking control. And here again in these papers, reinforcement learning is integrated with PID controller. PID controller actually it gives better results with the linear system when compared to nonlinear systems. And in the seventh paper, fuzzy logic is used. Fuzzy is used for the approximation of nonlinear systems. And in this slide, actually synchronization of the systems is considered. Synchronization of two nonlinear systems means the state trajectories of one system should follow the state trajectories of the other system. In that case, both the systems are said to be in synchronous with each other. And here for the synchronization, backstepping controller is used in paper number 8. And in the next paper, again backstepping controller, it is integrated with neural network architecture. The general basic neural network architecture. The difference between the basic neural network architecture and RNN is, in neural network architecture it is a feed forward system. It cannot store the past values, whereas in case of recurrent neural network architecture it can store the past values. Its hidden layer acts as a memory unit, so the present value, it depends on the past values. So during the literature survey, a few research gaps were observed, and they are mainly nonlinear systems. They will focus on integer. The existing controllers, they focus mostly on integer order systems. So stability analysis of fractional order nonlinear systems, it is still not fully explored. And conventional nonlinear controlling techniques, they require the complete knowledge of the system, like what are the initial states, what are the different design parameters of the system, what is the fractional order system, unknown nonlinearities present in the system, all these things. So, and sometimes these controllers may neglect the uncertainties present in the system, unknown dynamics present in the system, because of which they struggle to maintain the stability and performance of the nonlinear system. And because of unknown nonlinearities present in the system or uncertainties present in the system, these existing controllers are not fully reliable for real-time applications like secure communication and image encryption. These are the research objectives. First one is to analyze the stability results for fractional order nonlinear systems. In this, actually I have in this work, a nonlinear fractional order system is considered with actuator faults. Because of the unknown nonlinearities present in the system and actuator faults, the trajectories of states of the system will deviate from the desired trajectory, because of which error, which is called as tracking error, it increases. So in this work, 4 controllers are implemented on the nonlinear system and the results were analyzed. The performance is compared basically. Coming to the second objective, in this work, a backstepping controller is integrated with a deep learning architecture, that is recurrent neural network architecture. The recurrent neural network architecture is used for the approximation of unknown nonlinearities present in the system, and which inherently it uses optimization for optimizing the parameters and weights of the neurons. And third objective is it is actually in this work, the performance of the proposed controller, that is backstepping with RNN controller, is compared with existing techniques. That existing techniques are the basic nonlinear controllers, which are integrated with different techniques like reinforcement learning, eco-state network, fuzzy logic and all. And the last objective is about implementing the proposed controller for real-time applications, that is simulation based implementation only, that is for image encryption and secure communication applications. So coming to objective work, in this work, a fractional order nonlinear system is considered, whose state space model is given by expression 2. Here Vi of t represents the state of the system, H represents the unknown function, and G represents the known function of the system, and Fj of t, it represents the actuator output. And this unknown function H, it is estimated using the expression 3, that is estimated using regression function. And here epsilon I of t, it represents the approximation error, and regression is used to predict the variation of one variable with respect to the another one. And coming to actuator, actually it is the one which is responsible for the movement of part of the system. So this actuator generally, basically the general faults which occur in actuator are stuck type fault and loss of effectiveness fault. In stuck type of fault, even though a control input is applied, the actuator will not respond, it will not move it will not produce any movement. And coming to this loss of effectiveness fault, because of the fault in the actuator, the performance of the actuator, it degrades. So these two faults along with controller input are modeled as expression for, where fj of t is the actuator output, that is given by rho j theta j of t plus beta j fj of t, which is approximated one, which is the desired one, minus rho j theta j of t, where the value of beta lies in between 0 and 1. If the value of beta is 0, it represents loss of effectiveness fault. If the value of beta is 1, it represents stuck type fault. So theta j in the expression 6, theta star of t is the actual control signal generated by the controller, and this is applied to the actuator, and the actuator has its own gain and some imperfections. So along with the gain and imperfections and the actual control signal, it is modeled as theta j of t. Actuator is going to modify the actual controller theta star of t as theta j of t. And here this theta j of t again with going back to expression 4, this theta j of t combined with the fault present in the actuator, it is modeled as fj of t, which is the actual actuator output that is applied to the system. And the tracking error is the difference between the trajectory of the actual trajectory of the state of the system and the reference signal. And in this work, 4 controllers are implemented on the nonlinear fractional order system, and the controllers are backstepping controller, sliding mode controller, dynamic surface controller, and fuzzy dynamic surface controller, and the performance is analyzed here. So this is the general design methodology of backstepping controller. Here XD is the reference input. So at every state, the error is calculated, that is even in the first state, it is the difference between state x1 and the desired valued XD, and at each tracking error or at each state, a virtual controller is defined here. And to define the virtual controller, always we need the differentiation of previous controller here. So these are the general steps used in designing of controller using backstepping controller. So here X represents current state, desired states are represented by the vector XD, and time derivatives are represented by XD dot. And here tracking errors at each state are given by E1, which is E1 minus X1D. Similarly E2, where V2 is given by V2 minus alpha 1, where alpha 1 is the virtual controller defined at E1. And alpha 1 is given by minus K1 E1 and alpha 2. These are all the controllers at state 1 and state 2. To define virtual controller at state 2, that is given by the differential of alpha 1 minus K2 E2 and so on. So for the state model, what we have considered in expression 2, for that the error at ith state is given by expression 9, where omega Vi of t is the state at ith state, and omega bar suffix c, it actually represents the compensated signal, and the virtual controller at ith state is represented by omega bar I of t. Here in this expression, ei represents the approximation error, ki represents control gain, and zeta represents the regression function, and omega I minus 1 to the power of c, it represents the compensated signal, and h is the unknown function. And actual final controller is given by expression 11 here. And these are the general steps followed for the design of controller in case of dynamic surface controller. Here also the reference input is taken as XD, and error at each state is defined here also. But instead of differentiating virtual controller, its approximated version, that is alpha 1F, is taken, where alpha 1F is the output of the first order low pass filter. So like this, at every state virtual controllers are defined here. And here in this expression 14, it represents the actual controller generated by the dynamic surface controller. And in fuzzy dynamic surface controller, it is integrated with fuzzy. Here the unknown function is estimated using HI of t. This is the unknown function. It is approximated by W transpose. W represents the weight. It's a weight vector, and phi of t it represents the fuzzy basis function. And here the fuzzy basis function is given by expression 6. Where mu pi it represents the membership function. In fuzzy basis function, that is in expression 16, numerator it represents the firing strength of a rule. So the rule for which the firing strength is high, that is considered to approximate HI of t. Vi of t is the state vector, which is the input to this unknown nonlinear function, and output is expressed by expression 17. Here mu again represents the membership function, and the membership function is used as Gaussian membership function. And coming to sliding mode controller, for the fractional order nonlinear systems, the surface is defined as S of t equals to summation I is from 1 to n ki capital I t to the power of 1 minus alpha e suffix I of t. Here ei of t represents the error, and I represents the fractional order integral. And ki it is the coefficient of error here. It is a weighing factor for error. And here the controller generated by sliding control is given by expression 20. And here a sliding control is defined on which actually the trajectory should stay. So to make the states of the system to stay on that surface, this controller is defined by this controller. And these are the various design parameters used for various controllers. And alpha value is taken as 0.9 here, that is the fractional order value. And rho is considered here lambda 1, lambda 2, lambda 3, these represents the filter gains, and rho represents the actuator effectiveness coefficient, and K1, K2, K3 are the controller gains. And the initial states of the system, x1 of 0, x2 of 0, x3 of 0 are taken as 0.8, minus 2 and minus 1. These are the control inputs generated by sliding mode controller and dynamic surface controller. In sliding mode controller, to define the surface, we use a signum function whose value is either plus k or minus k. So sliding mode controller, it generates a discrete form of control input. In backstepping controller, the control input is dense because at each state we are defining virtual controller. We are trying to correct the error. So rapid error connection takes place. High frequency oscillations will also be there. And in dynamic surface controller, these high frequency oscillations, they are removed by using low pass filters. This is the tracking error, and the tracking error starts with a high value, and very soon they will be reduced to a minimum value. In case of backstepping controller, with minimum time it will reduce to minimum value. And this the system outputs for backstepping controller, dynamic surface controller with respect to the reference signal. So all controllers with they'll start with high tracking error, and BS backstepping controller, it shows means in this case it takes less time to settle down to the output to follow the desired trajectory, and error is also minimum. Settling time is also minimum in case of backstepping controller. It gives better results when compared to other basic controllers. In objective 2, here backstepping controller is integrated with an optimization technique, that is recurrent neural network architecture for fractional order nonlinear chaotic system with and without known system parameters. So this is a basic recurrent neural network architecture. It consists of 3 layers: input layer, hidden layer and output layer. And here the hidden layer acts as a memory unit for the neural network architecture. It stores all the previous values of the states, and so the current state, it depends on the previous values here. And here the unknown function is approximated using the expression fn. F represents the unknown function. This is equals to W transpose. W represents the weight matrix of neurons. Phi of H1. Phi of H1, it is a vector from the hidden layer. And here this W, the weight, this actually consists of generally the important parameters of the system. And the weights of the recurrent neural network are updated using the expression 22. Here W of k plus 1, it represents the updated weight value. W of k represents the current weight value, and eta is the learning factor, and W dot is estimated using expression 22, that is minus gamma phi of Hn into E, where E represents the error. Gamma is the adaptation matrix here. And here to estimate the unknown function, we need hidden state, and hidden state is evaluated using the expression 23, wherein here Hn is given by sigma of WH Hn minus 1 plus WX Xn plus BH. Here sigma represents the activation function, WH represents the weight vector from hidden to hidden neuron, and Hn minus 1 is the previous state. Wx represents the weight vector for input to hidden connection, and BH represents the bias. And for this, to compute this Hn, we need Xn, and that is a state vector. So state vector is evaluated using the expression 24. Here that is given by summation j is from 1 to I j, which is an activation function, and rho jh, it represents the weighing factor for the input uj, and vjh represents the bias. So initially Fn value is assumed 0 in expression 24. Later on, recurrent neural network updates the value based on the error present in the output. And this is the expression 25 represents this expression 25. It represents the control signal generated by the backstepping controller, and that is applied to the Genesio thesis system, which is a third order system. And here the fractional order taken is 0.94. And these are the design parameters. In Genesio thesis system, A value is taken as 6.2, B value 2.92, C value is 1.2, and D value is 1. And initial states are considered as minus 0.1, 0.5, 0.2, and the fractional order is 0.94. And the size of the hidden layer is 10, and the tangent sigmoid activation function is used because it is centered around 0. It gives smooth approximation. And the total data samples considered as 2000 here. That means the total input output data set, and that means different state values. And training data is 80%, testing data is 10%, and validation data is 10%. And the number of iterations are 100 here. Sorry. And here order of the fractional order is taken Q1, Q2, Q3, all the values are same 0.94, and if fractional order values are same, it is called as commensurate system, and if the orders are different, it is called as incommensurate system. And in this work, commensurate system I have considered. And the first figure number 8, it shows the states of the state trajectories before control signal is applied. And these are, figure number 9, it shows different control signals generated by basic controllers and the proposed technique, that is backstepping based controller with RNN. And these are the state trajectories when different controllers are used. In all these cases, state x1, x2, x3, the backstepping proposed controller, in case of proposed controller, they are settling to the equilibrium value. So when compared to the existing conventional controllers, the proposed controller, it gives better performance with backstepping with RNN optimization technique. In objective 3, the performance of the backstepping controller with RNN is compared with different existing techniques like neurofuzzy adaptive backstepping dynamic surface controller. In this backstepping dynamic surface controller is nothing but dynamic surface controller which is integrated with fuzzy logic and neuro is used to tune the parameters, and fuzzy logic is used for the approximation of parameters, and reinforcement learning integrated with backstepping control technique. Neurofuzzy is again integrated with backstepping sliding mode control, and eco-state network backstepping control, artificial neural network based backstepping control. In in eco-state network backstepping control, eco-state network is going to optimize the parameters, and backstepping controller is for designing the controller. And in the third one, neurofuzzy adaptive backstepping sliding mode control. Sliding mode control, it defines the sliding surface, and backstepping controller, it is going to define the controller, and unknown linear nonlinear function is approximated using fuzzy, and neuro is used for tuning the parameters. So here RNN controller, it is used for the approximation of nonlinear function so that it will minimizes the error present in this output, and for that mean square error approximation is used as an objective function that is defined by expression 27. Here x of k, it represents the state vector of Genesio-Tessie system, and x bar of k is the estimate, it is the state vector approximated by RNN, and n represents the number of training samples here. And this is the general procedure for, these are the general steps which are used to define the controller, to derive the controller in backstepping based dynamic surface controller. And here even error is defined at each and every state, and virtual controller is defined at each and every state. And here alpha represents the virtual controller, and V1, V2, V3 represents the virtual control signals, and V1F, V2F, V3F are nothing but the approximated values of derivatives of V1, V2, V3. In backstepping, we have the problem of explosion of terms, so that is overcome by using first order low pass filters in dynamic surface controller. So output of the first order low pass filter gives the approximated values of differentiation of virtual control signals. So final control signal that is generated by backstepping dynamic surface controller is given by u of t equals to minus f of x, which is the approximation of nonlinearities present in the system, minus k3 e3 of t error at third state, plus alpha into minus v2f plus v2. This v2f, it represents the differentiation, it is the approximation of differentiation of virtual controller defined at state 2. And in backstepping sliding mode controller, a sliding surface is defined as summation I is from 1 to n ki it to the power of 1 minus alpha ei of t. If alpha value is considered as 0.9, this value becomes 0.1, and controller defined as minus k1s minus k2 signum function of s minus f approximated version of f of x. Here k1, k2 are the gains, and the values are taken as 2. And the Genesio-Tessie system parameters are considered as 2, 2.1, 0.9, and the value of d is always, most of the time, it is considered as 1. And initial states of the system are considered as 1, and desired trajectories are given by sine of t, cos of t, and minus sine of t. And in neurofuzzy adaptive backstepping DSC or sliding mode control, fuzzy is used for the approximation of the system, and here unknown nonlinearity is represented, it is estimated using f of x equals to summation I is from 1 to n wi of x into minus ax1 minus bx2 minus cx3 plus d, where wi of x represents the membership function, and here the numerator, it represents the firing strength of the rule. And design specifications for this simulation are K1, K2, K3, the values are considered as 1. Initial system states are considered as 1 here. In reinforcement learning for event triggered backstepping control, here reinforcement learning is a machine learning algorithm which updates the parameters of the system, but instead of continuously updating the parameters of the system, it uses event triggering condition. So once the event triggering condition that is given by expression 34, when that is satisfied, then only it is going to update the parameters instead of continuously interacting with the environment and updating the parameters. Here TK represents the time instant at which the last time the control was updated, and sigma is a design parameter whose value is taken as 0.1. And in artificial neural network, it is a feed-forward network. It consists of input layer, hidden layer and output layer, but here there is no feedback mechanism. So neural network weights are adjusted to minimize the error present in the output, and here the unknown function is approximated by using the expression 35, that is f of x equals to w transpose phi of x, where w transpose represents the weights of the neurons and phi of x is an activation function whose for which the input is nothing but the state vector. So phi of x is given by the expression 36, and here weights are calculated using the expression 37, that is eta phi of x into E3, where eta is the learning rate, its value is 0.001. In eco-state network, it is similar to that of recurrent neural network architecture, where it consists of input layer, reservoir state and the output layer. And in the reservoir state, the weights are fixed, only we need to train the output weights. And here states of the system, actual states of the system are represented by vector x, and desired states are represented by y target, and output weights are calculated using the expression 38, w out equals to y target into x transpose plus alpha I, where alpha represents the it is a ridge factor, it is a regularization parameter, and f of t is approximated by using the expression w out into x u of t, where x u of t represents the reservoir states, and reservoir states are estimated or evaluated using the expression 40, where which is given by tan h of w input into u of t plus w into x of t minus 1. Here u of t represents input vector and x of t minus 1 is the previous state, and w in is the weight vector for the input vector, and u of t is given by 1 x1 to 10 power minus 4, and number of input states are 3 here, and these are the results of state trajectories for different values of initial states of the system. Here the initial states are considered as 1, 1, 1, x1, x2, x3 values, and here the values are considered as 0, 0, 1. So these here in this case the initial values are considered as 1, 0, 0. These are the state trajectories of different controllers. And figure 15, actually it represents the different control signals generated by various controllers integrated with the fuzzy logic, neural network, eco-state network, RNN and all. And tracking error is given by figure 16. And figure 17, it represents the time convergence, means when the trajectories will reach the desired trajectory is given by in this figure, time of convergence. And this is the comparative analysis of different control algorithms, where we can see the stability is more in case of RNN based backstepping controller, and convergence time is also less in case of RNN based controller, which is 1.38 seconds, and error tracking is also minimum, that is error will settle to the minimum value in 4.84 seconds in case of recurrent neural network which is integrated with backstepping controller. So here this performance analysis, it shows that the backstepping controller with RNN, it gives the better performance when compared to other controllers. So this proposed controller is applied in Objective-4 for real-time applications like secure communication and image encryption applications. So here generally in recent years the confidentiality of information, it has become an essential feature. So a secure communication system must be designed so that information signal or images, military images can be transmitted securely. So already we have a data encryption standard and advanced data encryption algorithms are already available, but these are vulnerable to cyber attacks. So therefore there is a need for developing a secure communication system based on the chaotic synchronization of fractional order nonlinear systems. A chaotic system, it produces a chaotic signal which has a behavior noise signal, the information signal also appears as if it is a noise signal. So in this mechanism, the key method, the key used is here. Here actually two systems are considered, two nonlinear fractional order systems, chaotic systems are considered. One acts as a master system and the other one acts as a slave system. And when these two are synchronized with each other, they will produce a same chaotic sequence. So at the master system, information signal is mixed with this chaotic signal and it is transmitted. On the other side, if the slave system is synchronized with the master system, it will also produce the same chaotic sequence that is subtracted from the signal which is transmitted from the master section, so that we can extract the actual information signal. But if at all there is a small change in the values, they are not going to produce, they will not be in synchronous with each other, so we cannot extract the information. It becomes very difficult for the intruder to extract the information. So this based here, master system and slave system both are considered as Geneseo thesis system, and expression 43, it represents the control signal generated by the Geneseo thesis system. And this is the block diagram of secure communication. Here master system has states x1, x2, x3, and these are chaotic states, and a chaotic sequence is generated by combining the states of the system, that is x equals to ax1 plus bx2, and this chaotic sequence is mixed with, this is combined with the message signal m of t. So s of t is the combination of m of t plus x of t, where x of t is the chaotic signal generated by the master system and m of t represents the message signal. So this is transmitted. Along with this, the controller of master system is also transmitted. At the receiver section, the slave system state trajectories should follow the state trajectories of master system, then only it is said to be in synchronous with the master system, and then only it is going to produce the same chaotic sequence. So at the receiver section, or for slave system, again a controller is designed which is similar to that of master controller, because if they are different, again slave system is going to produce a different chaotic sequence. And then the controller is actually used to make the trajectories of slave system to follow the states of the states of the master system here. So at the receiver section, when master system and slave system, when they are in synchronous with each other, so the chaotic sequence is generated by slave system, which is y equals to a into y1 plus b y2, and that is for decryption. This chaotic sequence is the chaotic sequence generated by the slave system, that is subtracted by the signal which is transmitted by the master system. So m dash of t we are going to obtain by subtracting the chaotic sequence generated by the slave system y of t, that is from s dash of t, that is the s of t is the signal which we have obtained from which we have received from the transmitter section. So in this way we can recover the message signal here. And here key signal must be transmitted, that key consists of the states of the system, initial values of states of the system, and the system parameters like ABC values and the fractional order of the system. So the controller has to make sure that the slave system will follow the trajectories of master system, so by achieving the same initial values and all. So in secure communication, x1 of t, x2 of t are chaotic signals, chaotic states of master system, they are combined, and the signal is x of t, that is mixed with message signal m of t. So s of t is the signal transmitted by the transmitter section. Along with this, master controller is transmitted and also key is transmitted. So on the other side, y of t is the chaotic sequence generated by the slave system. When slave system is in synchronous with the master system, so it produces same chaotic sequence, that is subtracted with s of t, the information signal. So if at all there is a small change in the values, the system will produce different chaotic sequence, because of which it becomes very difficult to extract the information signal. So this becomes very difficult for an intruder to extract the information signal if the person is not using the same values. Coming to this scheme of image encryption and decryption, here again two systems are used, master system and slave system. Both are Genesio thesis system in this case. So master system produces a chaotic sequence by combining the states of the system, and that is converted into a pseudo random vector, and again a pseudo random vector is converted into a key image K1, and original image is shuffled so that there is no correlation between the pixels, and this shuffled image between the shuffled image and this key image XOR operation is performed. So by that we are going to get the encrypted image E. And at the receiver section, again when master system and slave system when they are in synchronous with each other, the slave system is also going to produce the same chaotic sequence. Again that is converted into a key image K2, and again XOR operation is performed between the K image K2 and the encrypted image E to extract the image, and again that is shuffled and recovered the original image. So these are the steps followed here. So chaotic sequence X of t is generated by the master system, and that is converted into a pseudo random vector. That means which is not a true random vector. We can again generate the sequence. So this pseudo random vector is converted into an image K1, and XOR operation is performed between this key image and the shuffled image J. On the other side, at the receiver section, the slave system is also going to produce the same chaotic sequence Y, and the key image K2 is generated here, and XOR operation is performed between the encrypted image and K2 to extract the original image. And these are the errors and states of master and slave system when after synchronization. And this is the speech signal and its spectrogram. And 22 it it represents the encrypted message signal and its spectrogram. And this is the recovered message signal, which is almost similar to that of actual speech signal. And these are the results for image encryption and decryption. So original image is shuffled, and here 22 represents original image and its histogram, and shuffled image and its histogram. And when this encrypted image is when XOR operation is performed with the between encrypted image and the key image generated by the slave system, then we are going to get the recovered image, and their histograms are presented here. And here when compared to backstep, so here the backstepping with RNN controller is the performance of this controller is compared with the backstepping controller applied for these two real-time schemes. So the peak to signal noise ratio value is less in backstepping with RNN control. That means the signal looks like a noisy signal, so that intruder cannot extract the information, and mean square error is less in backstepping with RNN controller when compared to backstepping controller. Entropy is more, that means more randomness is present, so that again it looks like a noise signal, the original information signal, and correlation coefficient is less in case of backstepping with RNN controller. So in this work, when compared with the backstepping controller, backstepping with RNN controller, it is giving, it improves the parameters like peak signal to noise ratio, mean square error, entropy and correlation coefficient. But here the systems which are considered as same systems on both ends, at master and slave ends, and the orders are also same, means they are commensurate systems. But this scheme can also be applied to incommensurate systems. So in this research work, a backstepping with RNN controller is actually designed, and its performance analysis is compared with all the existing controllers. And so by observing all these things, backstepping controller, it gives the better results. A backstepping controller with RNN, it gives better results when compared to other methods. And this research work can also be extended to fractional order discrete time nonlinear systems and also for incommensurate systems. And here only implementation is implementation of the backstepping with RNN controller is considered without considering noisy channels or any disturbances, but we can actually test this under noisy channels. These are my publications, and one more is under review. Sorry sir, I forgot to mention here. Yes.
I assume that there will be some kind of evaluation board also, is it? Means some of you might be part of evaluation board.
Yeah.
So if any queries are
We had evaluated in three submissions, sir.
Okay.
We had done our work, sir.
Okay, great.
Okay, sir.
Ms. Narmada,
Sir.
first of all, you need appreciation for completing your presentation very smoothly and in flawless manner. Your slides were also okay, means they were not in excess nor too less. So optimum level of slides you have prepared, and you presented all the slides very nicely.
Thank you, sir.
As far as your work is concerned, in fact, I have given detailed description earlier, and I have seen your revised thesis also, and majority of the concerns which were there, they were incorporated in the thesis. I'm not sure whether at this stage also some corrections can be made. Means if some
Yes.
in thesis some corrections are to be made.
Yes, sir.
So one minor point is something which needs to be corrected. You just go through all your figures again, and there whatever variables notations you are using, legends notations you are using, they are not in consistency with what you are writing in the chapters. You are writing, say, x1, x2, x3 as variables. So 1, 2, 3, they are subscripts basically.
Yes,
But
sir.
if you see the legends, if you see the figures, again, they are not appearing in that similar manner. Right? So you just, maybe it may take 1 hour more.
Yes, sir.
You just go
I'll do
through
it, sir.
and just try to correct it.
Yes,
Because
definitely.
once this document is submitted, and it
You should find a
nice copy.
copy.
So please take care of it.
Okay,
and,
sir.
Maybe in consonance with the discussion with supervisor, you can correct it. Few queries which still I think you can pick them as your future work, because
Yes.
I have gone through the publication list. So a lot of scope is there where you can improve on publication end. Fine. Commensurate order.
Yes, sir, commensurate.
Stability of those
Yes,
systems that you have missed out means you can include that also.
Okay, sir.
One thing is, in all the chapters you have focused on one particular system, that is
Genesio Tessi.
and indirectly you are using backstepping approach.
Yes, sir.
So, maybe you are mixing it up with the deep learning, RML, and you are optimizing the controller. But then, if you see, focus of backstepping is towards strict feedback class of system.
Yes, sir.
Right? And this Genesio Tessi system is very simplified implementation of that class.
Yes, sir.
It's more or less triangular kind of system. But then if you take some other benchmark system which carries out justice with strict feedback class of nonlinear systems, then that can add further value to your work.
Okay,
Because
sir.
indeed, when you will communicate the papers, they will simply say, yes, theoretically your contribution is okay, but while validating those results, you are giving a very simple example. So they will not be in position to know whether these results are valid for that general class of strict feedback kind of systems or not. So that angle I think you can add.
Okay, sir.
One question related to the optimization. Once you are doing optimization and you are comparing different controllers, so while doing optimization, whether you are keeping all the parameters in different approaches similar for comparison?
All the parameters are same, sir.
Same.
Initial values, the system parameters.
You see, if you are comparing event triggering control
Sir.
to any normal nonlinear control technique, focus is totally different because even event triggering control challenge itself is a separate challenge.
Yes,
So
sir.
if event triggering kind of problem is there with us and I am applying different kind of controllers, then I am doing comparison. Then it is okay. But if I want to compare, say, plain adaptive backstepping or plain SMC with the event triggering kind of control, then situations are totally different.
Different,
Because
yes.
you know where we are using event triggering control. We use it where you are going to have some kind of external events which are affecting the system, or if inside the system also something is happening and your controller, which was supposed to communicate throughout with the plant, but then you are trying to leave your communication channel so as to just pass on information of the controller only at a selected sampling instance. So naturally then what focus is going to be that those events which are occurring in the system, we are targeting those and they are something which are affecting the system performance. So two scenarios are there. One is where some kind of internal issues or external issues are there with the system and we are forced to consider those issues because they are affecting the stability of the system. So we are using event triggering control, and added advantage is communication channel is relieved in terms of communication, use of communication bandwidth. But then if I compare it with the plain SMC, plain backstepping, then that comparison doesn't look nice. If you see, when we are comparing them, we need to put two settings at the similar place, then we can do comparison.
Yes, sir.
If setting is different, then
We can-
comparison, and we are saying that, okay, adaptive backstepping approach or RNN based backstepping approach is giving better results.
Yes.
That is a bit a loose statement. So just try to maybe improve upon it in the future work, because you can take it as another added problem where you are having similar setting with focus on certain kind of disturbances in the system, certain kind of events in the system which are very prominent events and they are going to affect the stability of the system, and then for that problem we are trying to work out different controllers. So that would be one way of extending the work. Go to the equation number 22. Equation number 22, I think,
Yes.
that is backstepping and RNN, where you are. Here, if you see, means you are updating the weights.
Yes.
Naturally, that is required in any learning technique. But then you are using W dot also.
Yes, sir.
So avoid this kind of means mixed kind of notations. Because you see, on one side it is something discrete upgradation. It appears like discrete upgradation of weights. Whereas W dot is the continuous differential.
Yes, sir.
Okay, so I'm not sure whether this is exactly what you wanted to convey here, or means this is implemented digitally also, this W dot.
No, sir. No, sir. It is not for discrete systems.
But this kind of representation you have picked from literature somewhere? Because
Yeah, from
this
Google
appears
only,
to be
sir.
mixed notation, discrete and continuous both are mixed.
Yeah, from Google only I have taken that
So,
tutorials point.
because W dot, if it has to be implemented in discrete sense, then it gives different appearance. It will not be like this.
I will.
So just
I will modify
take care of
that.
it, and if in cases by chance if it is there, just try to
Yes, sir. I'll
go
modify.
through. And one aspect is about quantification of the performance. When you're, I think I have put this in comments also, that if you're comparing different techniques, then when you say simply that error convergence is better in case of RNN based backstepping. But then if somehow we can quantify this, that in this sense, in timing sense or mean average sense, it is better, that would have been a nice way of representing the comparison. अगर आप third and fourth chapter है, I think where you are concluding
Sir.
That this RNN based backstepping approach gives better error convergence. But this better is again, it depends how you are tuning the parameters, what kind of setting you are taking. This better will become best for another setting.
Sir.
So either we should be representing this comparison in terms of some kind of table where we are saying that mean error is going to be this, or maybe timing of convergence, or maybe error
In
is
terms
falling
of
below certain
values,
threshold.
should I mention here, sir?
It can be mentioned, because once you mix these learning techniques with classical control techniques, then we need to be very careful about using these words best or better, or because we need to quantify them. That this is the way of comparison. Baki, in case of Genesio Tessie system, you are taking the parameter values differently also, ABC?
No, same values I have taken,
Throughout
sir.
same values?
Yes, sir.
Okay. For continuous time, I think these values are different. But it's fractional order version,
Yes,
values
sir.
are different.
Yes, sir.
This is what you are saying. Because somewhere you are writing A is 6.92, whereas at some other place A was something 0.9 or so.
I think once I'll check, sir.
Just see, because for chaotic systems, these parameters
Values
become
are,
very, very important.
yeah, for these values 6.92 will get the chaotic sequence. 6.2, 2.92, 1.
Chapters, if you
I
go
will.
further, somewhere you are writing A, B, C as 0.9, 0.7, 0.1, something like that.
Yes, sir. In third one.
A2.
No, sir.
Third
Actually,
one.
same values I have taken.
No. Don't jump to the conclusion hastily.
Okay. I'll check,
Because,
sir.
You see, one is integer type Genesio Tessie system, another
Sir.
is fractional order type.
Fractional order system.
So just see whether in literature these values are same, because we need to ultimately justify that it's a chaotic system. So for
Yes.
these parameter settings, system must be chaotic. If it is there, we can accept these values, no problem. But if it by mistake it is written like this, then we just correct it.
Yeah, okay, sir.
Right? And you have addressed here complete synchronization only.
Yes.
Okay. And you are putting some applications towards image encryption and recovery of image, and then maybe message recovery also.
Yes.
So in those applications, what are the conditions which you are imposing on the communication channel? Means channel is also important.
Yes, sir. But I have not considered them, sir. In
That you have not considered.
yes, sir. In future work, I'll try to.
So somewhere if you are putting all these things, then take one assumption, mention one assumption there that we have considered ideal communication channel.
Okay, sir.
Fine. Ideal communication channel, no fading is there of the signal, and faithfully it is transmitted from one end to the receiver end. Otherwise, those fading effects will also come.
Yes, sir.
Rest is, I think, fine from my side. Hopefully, you will be able to incorporate these minor changes. These are
Yes, sir.
minor changes. It will take.
Yeah,
maybe
definitely
1 hour
I'll do
or
it,
so.
sir.
You can just
I'll do it,
go
sir.
through it once. Rest, it's a fine work. Overall, it's good that you are able to blend RNN with backstepping, and it opens up another scope of doing work in chaotic systems also, and that is something new for me also. So I will also see what additional things can be done in this domain. Yeah, publication wise, I think you try to, because many results are there which you might
Yes.
not have communicated. So try to consolidate them also, and try to get more quality publications.
Yes,
That would
definitely,
be
sir.
one of the suggestions. Rest all is fine from my side.
Thank you.
So the process, whatever is there, we will complete. So if board agrees, because I am
Then totally on to you, sir. If you think so that everything is.
no, from my side it is okay.
Then we can call her as Dr. Narmada.
She presented the work nicely, and reasonably good work has been done in the thesis. So I congratulate Ms. Narmada, and we can call her Dr. Narmada.
Thank you, sir. Thank you, sir.
So it's fine. So you are working somewhere?
Yes, sir.